Okay, let's get started. It's a really great pleasure to introduce Tom Dror, sometime. So Tom did a bachelor here at the best year this institute knew so far. And then a master and PhD at Weizmann Institute, and soon she'll be leaving us for the US for a postdoc.
Okay, so thanks, Guy. And thanks, everyone. It's a real pleasure to be here. I haven't been here, I think, since undergrad, more than 10 years ago. So I'll be talking today about shallow convective cumulus clouds over the world's continent, which we call green cumulus cloud. And hopefully by the end of the talk, you'll have a pretty good idea about some of these clouds' characteristics and common properties, and so on. So just as a first glimpse, I'll remove the text here, and you can see, maybe, this is a snapshot taken from the International Space Center when it was moving above the western part of the Amazon basin. And these are exactly the green cube cloud, covering here massive parts of the Earth with the immediate effect on the albedo in the shortwave. You'll see also that they're very restricted in size distribution. These are small-scale clouds, order of 1-2 kilometers at the most. You can actually see here at the center of the image the Amazon River just by the absence of the clouds, and we'll maybe talk about it a little bit more later. So just a couple more visuals to get us going with the green cube clouds. Here are a sequence of snapshot images taken from geostationary satellites over the Amazon basin again, and this one was taken over continental US, showing us also the diurnal evolution of these clouds. So again, you see the extensive areas which they cover, but you also see how they form almost simultaneously and dissipate simultaneously as well. This is in a response to the very strong diurnal cycle that we have over land. But this was just a teaser. I want to go back to the beginning now, and the outline of the talk is that we'll start with a short introduction about clouds and climate. Later we'll focus on shallow convective clouds, and then focus even more on a specific kind of shallow convective clouds, which are, again, these green cumulus. And we'll talk about where and when these clouds like to form, the large-scale conditions, the meteorological context in which we observe them, and at the end of the talk, we'll focus a little bit more about the patterns they form and the organization of the cloud fields. So, as we know, clouds are affected by the climate, and clouds also feed back to the climate in what we call the cloud feedback. And we know that the cloud feedback can vary all the way from amplifying the initial warming perturbation to diminishing it, or at least offsetting part of it. And this has to do with the different clouds that we have, the different cloud classes or the different cloud regimes, where we know by now that high, less optically thick cirrus cloud, for example, have a larger effect on the longer radiation budget. And in the shortwave, they are almost transparent. And we're tackling low clouds, or these shallow clouds. These clouds have more effect on the shortwave. They have a larger albedo, and they're prone to more cooling effect because the difference in their top height temperature versus the underlying surface is very mild. So the cloud feedback, as is estimated today in the latest IPCC, actually acts to amplify the global warming, the initial warming perturbation. We have here the numbers and also the range of certainty. So it's very unlikely that we'd have a cooling effect from the clouds, that is, a negative cloud feedback. And this can be traced down to mainly three different mechanisms. The first one is the altitude of clouds. Basically, we expect with the changing climate that we have higher clouds. These higher clouds, as I briefly mentioned before, will trap more energy inside the system, leading to a warming effect. We also expect to have less of these shallow clouds, so in the amount, in the cloud fraction, would have less of the cooling clouds, will result in a net warming effect. And these two net warming effects are not fully compensated by the change in composition that we expect to have in low clouds in higher latitudes, in which we estimate that the ice crystals will melt into water droplets, which will reflect back more radiation. But quick parenthesis here, because this composition effect is also expected to be saturated at some point under global warming when we exhausted basically all this melting effect. So the way we go about estimating the cloud the cloud feedback is by decomposing it to the different contributions from the different cloud classes or cloud regimes. And this is, again, from the latest IPCC, just to show you the different kinds or the different examples of cloud fields that are, cloud regimes, that are estimated. And here's a comparison between the former IPCC and then the latest one from a couple of years ago. So focusing on shallow clouds, we can highlight the subtropical marine low cloud feedback and the land cloud feedback, which is actually dominated by the effect of shallow clouds over land. So to get some intuition into these different cloud regimes or cloud classes, let's take a look quickly at this random snapshot from a satellite showing us the Earth at a specific time. And if we think about it schematically, moving poleward from the equator, we are largely going through different large-scale conditions, different meteorological conditions that then dictate these different cloud regimes. So for example, closer to the equator, where we have warm water, we have the trade winds flowing, and we have, in result, the trade wind cumulus. These are very fine, small-scale clouds. Closer to the continents in the western part, and also further away from the equator, where colder water comes from the upwelling and the inversion is much stronger and pressing from above, we have the marine stratocumulus clouds. And these different cloud regimes then translate or manifest in very different patterns of the clouds. So while you see again, these trade cumulus may look like spread of sugar over the water, very fine scale structures, the marine stratocumulus have a very different structure. It's mostly cellular. We have open cells here, for example, with a lower cloud fraction, and here it's a part of closed cells of almost cloud fraction of 1. So when we look about these patterns, we can think about another feedback loop that has to do with the cloud patterns. We know that cloud organization affects the climate. You can think about it. We have a specific climate today, for example, which translate into numerous cloud controlling factors that will dictate the cloud regime that we'll see. And there are many such cloud controlling factors. I listed here a few. So the inversion stability, for example, the humidity in the upper atmosphere, in the free troposphere, and the surface wind, and so on. These different parameters then dictate the cloud patterns, and we see here from what we saw before that the cloud patterns are intimately related to the radiative properties, which will, of course, affect the climate.
You consider temperature as cloud controlling factor?
I'm considering temperature-related parameters like the inversion stability, for example, and so on. And then I would expect, under a change in climate, that I would have then also changes in, for example, the inversion stability and so on. So under a change in climate, we already know this from climate models, that we have changes, robust changes in, for example, some of these cloud controlling factors, and we can presume that they will affect the patterns in sort of a feedback loop. But we have several problems with this feedback loop. First one is that we don't really have a good and robust way to quantify cloud patterns. In the community dealing with this type of problems, we have more than 20 different metrics to evaluate the level of order in the system, in the cloud field. But we don't have, or we don't agree on one specific metric that everybody is working with. And the second one is that cloud organization, and specifically shallow cloud organization, It's not only not resolved in GCM because of factors like resolution and so on, it's not even being parameterized. So we cannot even start to think about how to answer the type of question that arise from this feedback loop. Going back to this table from before, so now we know the subtropical marine low cloud feedback are mostly the marine trade cumulus and the marine stratocumulus clouds. And this was a huge gap in our understanding that from the former IPCC until the latest IPCC a couple of years ago was managed to, as a community, we managed to close this gap a little bit. What do I mean by this? We had no available estimation in the former IPCC. Today we understand with fairly high confidence that the feedback from these type of clouds, the marine shallow clouds, is positive. Exactly because we expect less of them to form in a changing climate that will reflect less radiation and will translate to a positive feedback. In terms of the land cloud feedback, however, less progress was made, and we're still very uncertain about what is the feedback from these clouds. And this is the context for this work. So, again, going back to the snapshot, we now have some basic intuition about the context, the large-scale conditions, the different climatic areas that we are observing, the trade cumulus, the marine stratocumulus, but what's going on over land? How do we largely or generally characterize shallow convective clouds over land? We don't have a very robust and unified definition for this type of clouds. So what are continental shallow convective clouds? We often observe them over different land areas. We know that they root from thermals, those hot air bubbles that rise as the boundary layer builds up during the day. These are small clouds, optically thin. They are short-lived. They live about 20, maybe 30 minutes. And they are coupled to the underlying surface with a very strong diurnal cycle that can reach 10, maybe 15 degrees during the day, which is very different than what we see over the ocean. During this work, we mostly use observations. We are using the aqua satellite, the MODIS instrument on the aqua satellite, which provides us daily snapshot at the early afternoon, which is actually an ideal time for us to capture these cloud fields because many of the processes that have to do with the building or the development of the boundary layer get to their peak around this time. For the temporal variation and evolution of these clouds, we are using geostationary satellites. We're using the GOES R series, GOES 16, GOES 17, which, depending on where we're looking at over the land, can provide us with snapshots every 5 or 10 minutes. And we're not only using images, we're also using cloud products that combine some spectral information, both from the infrared and from the visible channels as well. So the first thing we wanted to do was to build a database of these type of clouds so that we can start to explore them. And we're looking at 3 different areas worldwide, which vary substantially geographically and also in their climatic conditions. So we're looking over the Amazon in the deep tropics. We're also examining this area over continental US, in the mid-latitudes, over temperate forests and many crop area. The corn belt is there as well. And even this northern area over this part of Eurasia. And we're looking at 4 different types of cloud patterns or cloud regimes, all the way from sparse, scattered cumulus. Some of these clouds get to almost clear sky conditions. Then we have these green Q clouds, which are, again, very restricted in their size distribution. They are aligned in sort of a grid manner with a tendency for linearity as well. We then have some transition from shallow to deep convection, and finally deep convective clouds. And we start to classify the images to these different cloud fields. I do want to emphasize here, or just note here, this classification test, which is inherently binary. We have to decide whether a specific picture will belong to a specific cloud class, is problematic by its nature because we know that clouds are transient entities. They are evolving over space and time in a very fast pace, especially these small clouds. So schematically, just to see our approach to it, you can think about many of these cloud properties, say the cloud fraction, the number of clouds in the fields, you name it, and plot the probability density function, just the PDF of this quantity, corresponding to the different cloud classes, and you will see that in the edges of the distribution, you might have some overlap between the different classes. We are aware to this situation, and we also account for it post-processing. Another thing to note here, that sometimes it's a small deviation in time or in space that will actually show a transition between the different classes. So you can think, for example, about these sparse fields as forming or dissipating green Q. Sometimes 20 minutes after this picture was taken, we can have green Q forming in the same place. And also, it's a small deviation in space. So you can think about a green Q field, but right adjacent to it, you have some perturbation in the humidity, and there you will see these transition clouds.
So just to clarify, the abscissa will be something like density of clouds or what bright pixels, I assume, in square area or along a line or in an area.
Mm-hmm.
And then this is special for particular time and particular
right.
or location.
Right.
It might change in course of time.
Right.
So this,
right.
As I say, very rapidly.
Right. Yeah. Yeah.
Similar question. So if I do plot like on the x-axis like cloud fraction or cloud height or whatever, will I see 4 modes of PDFs, or is this are these definitions contrived? Are these objective definitions that arise from the data, or it's just 4 bins in a relatively continuous distribution?
That's a good question.
It's a good question. You will not find 4 modes in. It's a very messy, noisy problem, and the approach here, like I said, it's binary. So we have to make a decision. I will give you a snapshot, and you have to tell me: is it sparse? Is it green Q? And so on.
No, so the question. So the answer is it's just 4 bins that
it's just 4 bins, and later we're looking actually. It's in a few slides that we are going to look how the data is really looking, and we're also accounting it for it post-process. So I'm going to mention in a few slides exactly how we do to tackle this sort of problem.
So the number of bins is somewhat arbitrary.
It's not arbitrary completely, because we have decided to take these 4 classes of clouds because these were mostly the clouds that we saw. We also had a different category that comprises of junk. So any pixel that wasn't classic or ideal, had a mixture of 2 specific patterns, went to the junk category.
Junk is the largest subsection.
Of course, yeah. But we're not limited in statistics. We have loads of data. So in order to avoid these false positive errors, we're willing to pay in a lot of false negative errors. So in other words, we're willing to throw away a lot of good data in order to make sure that we have the most classic, and still we expect this overlap. So let me show you real quick how we do it. So this is just an example of a snapshot over the Amazon basin taken. It's a specific snapshot, but it's actually quite a classic view of how the Amazon is looking during the dry season. Okay, so we're I didn't mention this yet, but we're looking during JJA, June, July, August, which is of course, summer in the northern hemisphere, and it's mostly corresponding to the dry season in the tropics. So I know some of you may expect these monster clouds over the tropics. During the dry season, it actually many times looks like this. So most of the domain here is populated by these green Q clouds, but if we take a closer look, we might see some areas that are more sparse in their nature. We might see some transition as well, and even here at the lower left corner, we have some anvils that are associated with the convective clouds. So we further divide this big domain into smaller sections that we call cloud fields. These are 1 degree by 1 degree, so roughly corresponding to a little more than 100 by 100 kilometers. And then each of these little 1 degree by 1 degree is classified to the different cloud regimes. And so we end up with a bunch of images like this that are visually classified, and we end up with a little more than 2,000 images in each category, and we have a factor of 2 more in the deep convective clouds.
How many jumps?
How many junks? Hard to remember, but it's around 6,000? 6,000.
6.
Yeah.
Do you have a picture of junk?
I don't have a picture of junk, but I can tell you that it's a mix of a lot of things. So like I said, sometimes we also, by the way, put in the junk the edges of the granule, because we only want to look right in the middle to avoid retrieval errors and biases. So it's this and it's pixels that have mixture in patterns, and it's pictures that are smoky, because we didn't want to deal with smokes as well. So we have a bunch of things there.
The clearance is also dependent on the magnitude of your square. If you took half a degree by half a degree, that would also change the...
Yeah, deciding on the size of this 1 degree by 1 degree was a trade-off, I guess, like many things that we have to choose. So again, it's arbitrary, but it's based on scientific consideration. So, for example, in order to detect or decide or to classify for a specific pattern, this domain cannot be too small, because we need to see repetition of patterns. It can also not be too big, otherwise we are prone to have a mixture of patterns. So we decided on this 1 degree by 1 degree that we'll also later talk to other breeds of other products, for example, Modis and Era5, as a compromise, but a good compromise. We did some sensitivity check there.
When you say classified, are these semi-objective or objective, or is this by eye or by...
The first work is purely visual classification, yeah. More? Okay, so the first thing we did after we finished this classification task was separate the different green cube clouds to the different areas over which we looked at, and simply look at the clouds. And when we look at them, it looks something like this. So we see that over the Amazon, over continental US, and over this northern part in Eurasia, mostly the green cube clouds look the same. The same in terms of their sizes, in terms of their cover or cloud fraction, in terms of the patterns, and so on. And this was surprising to us at first, because of this understanding that we know as cloud physicists that we expect different clouds or different patterns to form with different meteorological contexts. Like we've seen...
Is it it's by definition of the way that you select them that they must be similar?
Why? How come?
Because you select only a certain bin of size. You don't here you are doing you define the green cumulus at a certain size, a certain pattern, and others go to other classes.
We have all the other classes because these are the classes that we observe in these areas. It's not like we have other classes and we're not taking them into account. We might sometimes see stratus clouds, we didn't consider here because there were very, very little of them. When I say we didn't expect it, we didn't expect to see the same type of cloud patterns over the Amazon deep tropics, 10-meter canopy, over tundra in latitude 60. This was very non-intuitive, at least for us. And it raised a lot of questions. I hope I can answer them in the next section of these. So after this sort of qualitative observation, we wanted to really to gain some more quantitative understanding. And what we did was, for each 1 degree by 1 degree snapshot, we went to the MODIS cloud product and attributed MODIS properties to this specific snapshot. Exactly to look how the distribution look. And we looked at almost all MODIS properties. Here I'm showing you in this busy box plot just 4 of them. So let's walk slowly through it. So we have these different cloud properties. We have the upper row corresponding to cloud fraction, the lower row corresponding to cloud top height. cloud top height we mostly looked at to make sure that we're tackling indeed with shallow clouds, which we don't have some subvisible cirrus above it. And we're looking, the left column correspond to these actual properties, and the right column correspond to the standard deviation of these properties, which are also modest product. It's not something that we calculate. And we have the distributions of the different cloud classes ranging on the x-axis, and the different colors correspond to the different regions. So a couple of things to say about this. First of all, again, we see this smooth transition. So if you go to the edges of the distribution, you see this overlap I was referring to before. But still, if you look at the median and the whiskers, you see that generally they are well separated. This is one thing. And the other thing is, if you examine specifically the green cube clouds, you see that even within the different areas, the properties of the distribution look very similar to each other. And we can talk even more about their specific properties and so on, but I will not get into it now. Mostly want to say here that now, after this visual classification, we can use the statistics from this data set, and instead of continuing to visually classify, now use some statistics from these data sets to run over all MODIS years, 10, 20 years, whatever we want, and based on these properties, to then try to detect these clouds. And this is what we did next. We did it over 10 years, over all of the seasons, and we have the seasonality of the geographical spread of the occurrences of these green cube clouds. And you have here the different seasons, and I have marked in these white rectangles the areas over which we classified. And you see that these clouds are quite ubiquitous, forming over our hotspots where we initially looked for them, but also in other areas as well. And let's focus now on the JJA season, because that's when we see them mostly forming. And the color bar here ranges in percents. And we see that, for example, over the Amazon, these clouds are forming almost values getting up to 30%. And this is actually a lower bound estimation because the post-processing eliminated most of the distributions. So we're mainly focusing on these median and between 25 and 75%. So all the overlap that we've seen before was thrown to the garbage. So now we're only looking at the very center of the distribution, and this was done in order to further clean up this data set. So we see them over the Amazon, we see them over US, over other continental areas, and we know that they are there many times during the dry season. Bear in mind this map, and now I'm showing you just the global distribution of the world forests and other vegetated areas. And you see it's not entirely correlating, but there is a big affinity between these two maps. So green Q like to form over green surfaces. This is why we refer to them as the green cumulus. And when we check specifically the land covers over which they like to form, we see that mostly they're forming over forests indeed, but not only. They are forming, we see them over shrubs, crops, grass, and so on and so on. Okay, so this is the first, just summing up this first section, going back again to the satellite images from before, the trade cumulus, the marine stratocumulus, and now we know that we have this green cumulus. We know more or less where and when they like to form, our hotspots during the JJA season. And now I schematically just plot the equator again. And Danny, this goes back to the little discussion we had before. So while we see the red areas of the trade queue are located symmetrically around the equator, in a very specific confined environment, and the marine stratocumulus as well, the green queue are spread more further away from in different conditions. So this was what we were after next. What is this blend of large-scale meteorological conditions that allows the green queue to form or to prevail over such a wide variety of geographical environments? And in order to do this, we wanted to increase our statistics, And so now we use this visual classifier from before as a baseline to train a machine learning algorithm so we can really upscale the analysis and probe much more images. And it worked up pretty good. So instead of probing 1,200 images or so, we're now probing much more images, almost 500,000 images. Instead of 2 months, we now span the period of 10 years, and we end up with about 90,000 GreenQ images instead of just 2,000. And here I'm showing you just a few examples for model predictions. The model did a pretty good job in detecting these clouds. And the first thing we did after we finished this task was very similar to what we did with the MODIS dataset, was attribute now LF5 properties, so reanalysis properties, to each of these different snapshots of, again, 1 degree on 1 degree. And this is what I'm showing here. So going from left to right, we're looking at the atmospheric profiles of potential temperatures, specific humidity, relative humidity, and the large-scale vertical velocity. And the different colors correspond to the different cloud classes, going from sparse to GreenQ, transition, and deep convection. And this pops up again here because also in terms of meteorological conditions, we see that we have this very smooth transition. So not a separation of modes, something very continuous that is hard to separate sometimes. And let me focus here on the relative humidity and the vertical velocity. The relative humidity is very easy to, because it's normalized, it also contains representing both potential temperature and specific humidity. And we see that generally, going from the sparse to the GreenQ and so on, we transition from a hotter and drier atmosphere to a colder and moister environment. And in terms of the large-scale vertical velocity, we are mostly moving from an atmosphere that is dominated by subsidence to a different atmosphere in which the sign change from subsidence to large-scale lifting is happening in a higher and higher altitude. If we unpack this green curve of the GreenQ to the different GreenQ in the different locations, here in the different colors, we see that in terms of relative humidity, we have really a convergence of their profiles. We do have some slightly different profile in the Amazon, and we attribute it mostly to the fact that the atmosphere is puffier over the Amazon, and its latitudinal dependence as we go poleward and poleward.
What is puffier?
I mean, the height of the tropopause above the tropics will be around 18 kilometers, where as you go increase in latitude, it will become smaller and smaller. In terms of large-scale vertical velocity, we see that throughout most of the free troposphere, we have this large-scale subsidence, which is dictating the inversions, and we have very mild updraft or large-scale updraft in the boundary layer. These conditions together then dictate the type of cloud or the cloud regime and the location of the clouds on the vertical. Focusing now on the Green Cumulus organization, again, just a random snapshot over the Amazon and showing this linear curved linear cloud streets. And these cloud streets correspond to the wind pattern or the mean wind pattern in the convective boundary layer that you can see here in the squiver plot to the right. So we have the trade winds flowing. They flow into the continent. They then hit the Andes, forced to go down, and along with it, they curve the patterns of the clouds. A different perspective on it is taken here from a plane where you see the clouds form in tangent to the wind, and again you see the clouds are absent over water bodies. These water bodies are colder than comparing to the land surface during the JJA seasons, which induce downdrafts over these water bodies, and so we don't have the clouds forming there.
That begs to check the latent and sensible heating rates.
Sorry?
That begs to check the surface energy fluxes, latent and sensible.
Right. Actually, we did do this. I didn't show it. We can talk about it maybe later. But
why is it less important than the other things then?
It was less important than the other ones because it wasn't as discriminative between the different patterns, as we've seen comparing the relative humidity, for example, and the wind speed. But this can be due to non-physical reasons that has to do with resolutions or not enough statistics or very similar distribution. My guess, and I say guess because I didn't yet examine the specific fluxes, surface fluxes, not from in situ measurement and not yet in the model, is that it will of course be a very important factor.
It's visible here. The fluxes from the water is less.
Exactly.
Yeah, it's visible that it discriminates between clouds and clear sky, but not between the different cloud types.
Yeah.
So before she showed things that discriminate between the different cloud types.
When you have deep clouds, there is no such discrimination, I believe.
So the problem actually that we had with the deep clouds is inherent to the methods that we use, which is satellite data. So when we have this top-down view, and what we obviously we see just the upper layer of clouds, many of the cases were actually many layers of clouds. So you could have in the boundary layer this green cumulus, but then you have other layers. You're categorizing them as deep convection clouds, but the boundary layer has all the properties of the green Q, and we cannot take it into account. This was part of the problem, which comes from the approach. Okay, so this is a movie. Yeah, it's a movie showing the same episode, the same day I showed in the very beginning over continental US. This is how it looks from the raw data, or more or less the raw data. We're looking here at reflectances from the GO 16.5 kilometer resolution, snapshot every 5 minutes over the US, and you see this diurnal evolution of the green Q clouds that we talked about before. So yeah.
Sorry.
No, go ahead.
So these appeared diurnally. At what time is this? In the afternoon, noon, early morning? When do they?
So you have a local. These are very lazy clouds. So we observe them forming 10, 11, very late morning. They take time to respond to this heating of the solar heating of the surface. Then they start to form. They peak around the early afternoon, mostly in agreement with the MODIS time. Around 2, we see their peak. And then as the evening approaches and the surface cools down, they dissipate.
So it follows more or less surface temperature, maybe?
Yes.
But wouldn't this be out of phase with relative humidity, which would actually be lowest? So what's the controlling parameter? Is it temperature or relative humidity?
So they need a combination, of course, of both of them, and it's also a delicate combination because we've seen this smooth transition between the different patterns, right? They need the exact amount of humidity to allow them to form. If they have a little bit excess humidity, they can transition to something more clustered or even to deep convection. This, by the way, sometimes happens in the afternoon in the US. For example, in the southern Great Plains, you see many transition from shallow to deep convection in the second half of the day. This is mostly due to humidity perturbations. So it's not only temperature controlled. So forming around 11, 10 in the morning, already at 5 they are gone. So it's a very short sample of measurements that we have from the satellites. It corresponds to sort of a three-dimensional matrix of longitudes and latitudes horizontally, and the third dimension is the time. So like I said, we have about 8 hours of measurements corresponding to about 100 snapshots, and the first thing we did was take just the time average field or the mean field, which is basically, if you think about it pixel-wise, just averaging the pixel averaging reflectance over time. And this is the image that we get of the averaging 100 different snapshots. So these green cube clouds, they are small, they're living for maybe 30 minutes, but somehow the patterns that they're forming manage to sustain. We do see some drifting or meandering, but we're still clearly seeing this linear alignment even though we're averaging so many hours and so many images. So this is just as a first indication to how stable or ordered this system is. And here are a few snapshots of this diurnal development. So you see also this, the times, and almost local. This is Eastern Standard Time. We are covering a few time zones here. So now what we're doing is subtracting this mean image in time from each of the different snapshots that we have in reflectances, and we end up with reflectances anomalies. So here the reddish colors correspond to reflectances positive anomalies or positive perturbation from the mean, and the bluish colors correspond to negative reflectances, negative anomalies, sorry. And it's these reflectances anomalies that we then use as an input to an EOF decomposition. So briefly, EOF corresponds for empirical orthogonal functions. It's a mathematical decomposition. It's equivalent to a PCA, principal component analysis, and it's often used in climate science and also in atmospheric science to try to extract dynamical modes that exist in our data sets, okay, and to try to separate also between the different frequencies. Important thing to note here is that, again, it's a mathematical decomposition with a very strong constraint of orthogonality. And we already know that very little things in nature, and for sure in clouds, are orthogonal to each other. This is a very strong constraint, and it will make any physical insight not trivial at all to gain from this decomposition. Nonetheless, we're going for it, and we're plugging these reflectances anomalies snapshots that we have, and we end up with EOF modes that are these structures that are frozen in time, and we have the principal components, the PCs. Here I plotted 20 of them. You can see the sorting in the frequencies that we have, mostly going from low diurnal evolution to higher and higher frequencies. And the EOF allows us then to sum up the multiplication of each EOF mode by the corresponding amplitude of it that is provided by the PC at a specific timestamp to reconstruct the field then. And we're summing over the modes. We have 20 modes. The 20 modes correspond roughly to 2/3 of the variance of the data set. So just as an example, this is a snapshot of our field from data. And when we sum up all the modes from 1 to 20, multiplying the EOF by the PCs, this is the reconstructed field.
It's the anomalies.
This is, first, you're right, first we sum up the anomalies, but then we add the mean field back. Yeah, so this is the entire field. And we're looking at, again, this is the amount of the variance explained, but mostly we're capturing the clouds and even some other features as well that I will focus on later. We decided to focus on this red section, which is orthogonal to the cloud streets. It's 1,000 kilometers, and we wanted to examine the diurnal evolution of the field as it's advected throughout this red cross-section. And we're looking at this sort of Hofmuller representation. So here we have the data, which is, again, reflectances. On the y-axis we have time, and the x-axis is just distance along this red cross-section. And this is a pretty noisy plot, but we mostly see, for example, the diurnal cycle going from low reflectances in the morning. Then we have the clouds forming, dissipating along this section. And again, we see the low reflectances as the day progresses. But the EOF allows us to reconstruct the field, not only summing all the modes, but also trying to separate the different frequencies. So for example, if I reconstruct the field using only the lower frequency modes, modes 1 and 2, and replot this Hofmuller, suddenly I see the cloud streets are much more pronounced. They're not blobby anymore, they're continuous, they're vertical, exactly orthogonal to the cross-section. And from this representation, I can try to estimate some of their properties, for example, their wavelength or their aspect ratio, and try to estimate it. Actually, we get values that agree very well with the values reported in the literature for continental cloud streets, for Rayleigh-Bernard convection, and so on. Moving then to the intermediate frequencies, we see that when we sum them up, we have a different alignment. We have this horizontal alignment. This alignment corresponds to gravity waves that travel throughout the fields. We can estimate their periods, also agreeing very well with the literature. In fact, if I show you real quickly the movie from before, and please focus in this area in the afternoon, you might see these gravity waves passing on top of the cloud fields. I have marked the corresponding EOF structures of mode with this dashed line so you can see their presence. It's very delicate. I don't know. It's okay if you don't see it, but it's there. Getting to the final high-frequency modes, modes 10 to 20, these guys oscillate in a very high frequency, which is also constrained in time to the time when the green Q are appearing in the field. And when we plot the corresponding half-molar, we see exactly the clouds. So this is not noise. These are the green Q clouds. They are forming and dissipating along the cloud streets, but they are also forming and dissipating in a synchronized way on the horizontal axis. So you can see green Q clouds that are far in adjacent cloud streets that can be hundreds of kilometers away from each other, and still it seems there is some coherence in their formation and dissipation during the day, insinuating indeed on a very organized grid of clouds that we're observing, which is much beyond the single cloud or the parcel model that we used to think about it. So just compiling all of this information from the EOF analysis, we were able to actually infer some physical insights from the mathematical decompositions. We see that we managed to separate the frequencies, these lower frequency cloud streets, the gravity waves that pass through the field, 1, 2, maybe 3 gravity waves in the afternoon, and the actual cloud themselves forming during the day in a very organized way. So just to sum up, and again going back here, so we now know, or I hope that you have a better idea of shallow convection over land, about these green Q clouds. We know more or less where and when they like to form. We know the context of meteorological conditions in which we observe them, this combination of humidity, large-scale subsidence, strong inversion. We now also have some idea about their patterns, mostly grid-like regular pattern, which has a linear alignment to it. And going back to this textbook representation, which we all know from our history at some point, there is this correlation between the spatial and temporal scales of many atmospheric phenomena. So all the way from dust devils in the microscale through cumulus clouds and to the synoptic scale, generally they fall on this linear curve on a log-log plane without very big perturbations to it. So today we've focused on these cumulus clouds. Again, order of 1 kilometer, living for maybe half an hour. But we've also seen that together they form this new entity that we call organized cumulus field. And this organized cumulus field is comprising of these single cumulus clouds, but the self-organization of the field really allows for this big leap in scales between the single cloud and the cloud field. And this is enabled through the organization and the synchronization of the clouds. A quick outlook. I will not go much further into it, but